Thanks, Julian, for the nice introduction, and I'm glad that the committee invited me. Excited to be here. As Julian said, I'm a postdoc at Princeton and GFDL, and I'm part of a project called M Square Lines, where the overall goal is to improve climate models at the air-sea interface using data-driven techniques. And Julian is also one of the PIs, and in this room there are other two members. There is Alexis and there is Marcel. Hope I'm saying the name correctly. And so I'm going to talk about modeling vertical diffusivity for the upper ocean boundary layer using machine learning. Yeah. And so these are the key points of my talk. As in, I'll get into details in the forthcoming slides, but the key points are that at GFDL we had a baseline vertical mixing scheme, and when I ran a control simulation, I found out that the baseline scheme exhibited some bias in the mixed layer depth. And in this first plot that you see over here on the right is the summer mixed layer depth defined by the minimum of monthly average mixed layer depths. And I'm comparing about 15-year average with Argo data. And we can see that in this simulation, the model is predicting a deeper mixed layer depth in the equator and near the equator. And you see this by this blue shading over here, right? So the control scheme predicted a deeper mixed layer depth. So in my work, first I wanted to explore what happens if you bring in some complexity from a higher order moment closure into a coarse climate model. And I employed neural networks which learned the diffusivity from a higher order scheme. And I implemented that in MOM6, which is the climate model used at, or the ocean model used at GFDL. And when I switched on those neural networks, the bias near the equator significantly reduced, and you can see that the dark blue patch in roughly plus minus 30 degree is significantly reduced. On an average, there is a reduction. This showed us that improving the boundary layer physics through neural networks did end up in reducing some biases. And my recent work, I've been attempting to replace the networks with equations, because there are two problems with neural networks. As in, one is that it's a black box, so we cannot interpret what is exactly happening. And plus, I found out that there is also an increase in the cost when you use a neural network inside a GCM. And so the cost is not very high. It was about roughly 5 to 10%. But for a production level, it could be high. So the next step has been that if I could replace the networks with approximate equations, which showed similar skill as the networks, then maybe if the bias is also reduced, then we can probably interpret them, because now we have equations. So this has been, so I'll get into details of all of this, and I'll give some background. I know this is the last day, so I hope you guys are awake. Um, the plot on the right shows a sketch of various spatiotemporal dynamics present in the ocean. The x-axis is spatial scale, the y-axis is temporal scale, and in this square white colored box, we see the features that are resolved in climate models, such as basin scale, variability, El Nino, etc. And as we go down, we have subgrid processes such as mesoscale processes and submesoscale and vertical mixing, which are not resolved, but they need to be somehow parameterized. Currently, we are trying to get into this mesoscale resolving or permitting regime, and these subgrid processes are represented by the right hand side in this equation. So the right hand side has some unknown terms, right? So this is a turbulent flux, and we do not know exactly what should be the right equation for these terms. So this is one challenging aspect in terms of ocean modeling. But climate models are getting better eventually. So this plot over here shows the evolution of the lateral grid size in climate models. The x-axis is years, and the y-axis is grid spacing in log space. And these dots represent different CMIP experiments, and they are roughly following on this scaling relationship, which you can say this is like the Moore's law for CMIP. And so they are approximately following this Moore's law, but we know that we are going to hit some sort of limitation, because Moore's law seems to be limited. Uh, but in a idealistic scenario, if you extrapolate this relationship, then the vertical mixing processes get resolved in 2090. So not in our lifetime, and we know that climate change is already happening right now. Uh, but this is hypothetical, right? And we are already over here, somewhere where we are hit a boundary or a wall, whatever, and we know that all of the missing processes need to be parameterized as accurately as possible. But there are problems with parameterizations, as in, if there is a paper by Lehner et al. 2020 where they have partitioned how much uncertainty is due comes from various sources, and this blue patch over here shows model uncertainty, and this is the lead time in years, and the green patch shows scenario uncertainty. And we see that the model uncertainty, which could be because of uncertain parameterizations, is roughly as close to scenario uncertainty. So scenario uncertainty is, we do not know how much CO2 will be emitted, and so we have different scenarios. So there is some uncertainty in the projections. And so this model uncertainty comes from, one possible source of model uncertainty is subgrid parameterizations. And so, for example, in the previous talks, we have seen various ways of formulating equations for vertical mixing. So, for example, there is a turbulent flux which is given by this eddy diffusivity hypothesis. There should be a minus sign here, but anyway. And in Birita's talk on Monday, we saw that what happens when you have two ways of parameterizing the same thing, as in you have eddy diffusivity, and on top of that, you can also add some non-local terms, and you could see some disagreement or some agreement due to those choices. And in Marta's talk, you saw parametric uncertainty, as in you know the equation, or you assume that equation to be correct, and you optimize some parameters. And there are you could choose any of these, right? And these kind of choices can lead to uncertainty, which contribute to this model uncertainty. So it's important to reduce this model uncertainty, because scenario uncertainty might still exist, but if you can reduce model uncertainty, then we could build up more trust in climate projections. So my work has been trying to attack the problem of upper ocean mixing, as in this mixing involves what we call as isotropic turbulence, and the upper ocean. So the audience are very familiar with upper ocean, and in short, the upper ocean exhibits certain special characteristics, as in it has a well mixed region, and it is seen in throughout world oceans, as in this patch is equator, this transect is in the Arctic Ocean, and the upper region is well mixed, and that is due to presence of multiple turbulent processes. And this upper ocean is modulated by shear driven mixing, convection driven mixing. There are some wave effects, and we also have some restratifying effects, which are opposite to these kind of mixing effects. And all these various effects contribute to mixing in the upper ocean and deepening of the mix layer, and they modulate the sea surface temperature. So it's very important to simulate these processes as accurately as possible. And there are various ways in doing this, but a common assumption employed is the assumption of 1D process. And what we care about is that this is a vertical transect of an LES simulation, but we do not care about these individual eddies that you see over here. We care about some average evolution of the boundary layer. So how does, let's say, this fluid in this boundary layer depth H evolves over time, and to simulate that temperature or any tracer in that upper ocean, we usually have some evolution equation where we have a time derivative of some tracer. I'm showing temperature over here, but it could be temperature or any other tracer. And on the right hand side, we have a divergence of flux term. So, and if you assume the eddy diffusivity in this case, then it comes down to a 1D sort of a diffusion equation with the appropriate boundary conditions. And when you evolve this equation, then you can assume that you're getting the evolution of the 1D processes. And now the question is, what is this diffusivity kappa? Because that is not constant, and this kappa is given by some length into some velocity. And broadly speaking, there are two ways of getting to this kappa. So there are some schemes called prognostic schemes, where you evolve the turbulent kinetic energy budget, and that is given by some source and sink of these turbulent kinetic energy, and from there you can recover kappa. And there are the other class of schemes are called diagnostic schemes, where there is no evolution of any quantity. You directly obtain kappa using some assumptions. So for example, the KPP scheme, which is a very well evaluated scheme, could be considered as a diagnostic scheme, whereas the scheme used in NEMO could be considered a prognostic scheme. And there are also some higher moment closures, such as second moment closures, which are formulated in this way. But there is a problem, as in you can have various ways in getting kappa, and there is a lot of disagreement in those. And this is a paper by Lee et al. 2019, and there are many subplots over here. I won't get into the details, but the key point is that there is a reference mixed layer depth, and all the other plots are done by simulating or using a different kind of boundary layer parameterization, and all of them sort of disagree in the magnitude as well as the trend. So the red means I think a deeper mixed layer depth bias, and the blue is shallower, and you can see there are blue and red shades everywhere. So they disagree on the value as well as the trend. So this is the problem, as in they all disagree. But what is more concerning is that if you just look at these two plots, they are both KPP implemented in different model, or in a different kind of algorithm, whatever, and they also disagree. So even the same scheme implemented in different models can disagree. And so this has been an issue, right? That we do not know which one is correct, or even if that's a good question, I do not know that which scheme is correct. To reduce some of these issues regarding energy conservation and stability, etc., GFDL devised its own scheme called the Energetics Planetary Boundary Layer Scheme, or the EPBL scheme. It has been documented in a paper by Reichel and Hallberg in 2018. And the key point of this scheme is that the rate of change of potential energy has been parameterized. So this scheme parameterizes conversion of TKE to potential energy using some parameterization, and by and from this parameterization you get an estimation of the boundary layer depth H. So when I started working on this project, I first looked at what happens if you change a single parameter, and I changed gamma, and this gamma parameter comes into this diffusivity through the length as well as the velocity scale. And so the way this works is that you somehow estimate the correct boundary layer depth based on energetics criteria, and after that you impose some diffusivity profile between the surface and the boundary layer depth. So I just changed gamma from 1 to 3, and I looked at some metrics. So I looked at ocean heat content, and it turns out that the rate of change of ocean heat content has a lot of disagreement, and this disagreement is by about 0.15 watt per meter square. And so this means that even the same scheme, if you change one parameter, it can disagree by a lot, and this is concerning, right? Because then which is the right value of gamma? And so here I want to make the point that these schemes should be more data driven or more constrained on physics, and probably you can target this. You can think of this as parametric uncertainty as well, as in, can we get to the right value of gamma to get the right ocean heat content, for example. But I approach this from a different point of view, as in, can we just replace all of these parameters by directly emulating something coming from a higher moment closure? So here's the challenge, as in, the plot here shows the diffusivity profiles, but they are normalized by their magnitude. And in diagnostic schemes, generally we have this black dash dot line, which doesn't respond very well to forcing, as in the structure of this diffusivity remains almost the same. But if you look at the same diffusivity in higher moment closures, there is some response to forcing, as in the location of this maxima might change, and the magnitude might be as per some TKE based equation. And so this is ideally what we should be using, but we are stuck with these kind of schemes. and that's because there is a time stepping constraint. As in, if you roughly put these schemes on a accuracy versus cost plot, then these better closures, or the so-called second moment or higher moment closures, would fall somewhere way up over here, where they have very high accuracy, assuming that's the ground truth. But the cost to use them in GCMs is also very high. So we require a time stepping of maybe 10 seconds, 1 minute, or 5 minutes for these kind of closures. But when we run a climate model, we want to go for a longer time step, because we want to run climate timescale simulations, as well as we want to run them in ensemble settings. And so these diagnostic or first order closures are over here, and this is where I'm showing KPP and APBL, and we can run them with maybe 1 hour time step or 30 minutes time step. But with machine learning, we can at least bridge this gap up to some extent. As in, with machine learning, we can move along this line where we are going with the same time step, and but we are having better accuracy. Uh, but then, why is this possible, right? And so, for those people who do not know neural networks are just some sort of an advanced version of linear models. In linear models, you have these linear kind of relations, but neural networks are non-linear, and they have these non-linear operators between these linear models. And with this non-linearity, you can map non-linear relations between your input x and your output y, and this helps us in modeling non-linear features. And neural networks are not new to earth sciences, as in they have been used in radiation schemes in 1998. And recently, a lot of neural networks a lot of research has been done in how to implement neural networks, or check the impact of neural networks in climate models, or weather models. And here are some examples. And so the capability of neural networks in allowing us to map nonlinear relations can help us in this way. And the way neural networks can be used in subgrid modeling is by following the traditional approach, as in, you have some inertial terms on the right hand side, or some evolution terms, and on the right hand side you have these subgrid terms. If you make neural networks learn these kind of subgrid terms, then you're still following the framework of maintaining conservation laws, and this is the way traditional parameterizations have been formulated. um, and in this way, you can conserve some quantity, so you're still within your traditional framework. And this sort of method is called hybrid modeling, where some portion is calculated in the same traditional way, whereas the uncertain subgrid fluxes are determined by using some machine learning techniques. And so this is the background of using neural networks in for subgrid modeling. And so for my work, I wanted to use neural networks to try to bring in higher order complexity in a first order closure. So I first created my training data using a GOTM package, which is this single column model configuration, and I use a second moment closure scheme. So I used Capsulon, and I generated training data by varying the forcing as well as the latitude. So I varied wind stress, I varied surface buoyancy flux, and I took neural networks and I made them train on that data. And in the first order closure, I replaced two components in the diffusivity. So I decomposed diffusivity into these three terms. One is G sigma, which is the vertical structure of diffusivity, and it goes from 0 to 1, and this is non-dimensional. Then the second term is the boundary layer depth h, which is based on the physics-based scheme, and this comes from the energy criteria. And the third term is the velocity scale. And in this decomposition, only the first and the third term have all the uncertain components in them. And I used two neural networks which predicted these components from better data. And I did not touch h, because h comes from a physics-based scheme. And if you know it's based on physics, then you should not touch it. So by having two neural networks and multiplying them with h, you can recover diffusivity, which was supposed to come from a second moment closure in your ocean model. And so this kappa is substituted in the EPBL mixing scheme in MOM6. And here are some single column model results. The key point is that once the networks are switched on, the EPBL scheme in MOM6 gives a similar kappa and the stratification compared with k epsilon in GOTM. So that's the key point. And this is a single column model result. So this is only vertical dynamics. But this is the result that I showed in the first slide. As in, I ran this scheme in MOM6 in its quarter degree configuration, and this is forced by JRA product. And we are looking at the summer mixed layer depth, and this is what I showed. As in, there was a reduction in the bias in the tropics, so the at this point the improvement happened because the neural networks probably enhanced the physics happening in the tropics or other parts as well. But then the question is, can we interpret what the networks have been doing with equations? And I will show you how. And then we can replace the networks with equations. So how much time I have? Like 5 minutes or something? Or? 5 minutes. Okay, yeah. And so so to replace the networks with equations, I tried some various equation discovery techniques, and I tried something called as symbolic regression or genetic programming. I won't get into that, but in short, it is an algorithm where you throw in the data and it sort of goes into this brute force, semi-brute force technique where it gives out an equation. And it goes through some tournaments where it decides a winner and a loser of those expressions, and then it combines them using some algorithm. So I won't go into much details, but this is a nice technique, but this is very challenging to use because sometimes it works, sometimes it doesn't work. And so I had to try different techniques, but I also tried the old method of looking at the data and doing empirical fitting. So the genetic programming or symbolic regression gave a nice equation for this velocity scale under surface heating conditions. But for surface cooling conditions, I did not get a compact expression which was easily interpretable. But overall, I was able to get a nice fit between the prediction from these equations as well as some ground truth. And just to show you a cool video, this is how, so the green dots are data, and this is how symbolic regression is trying to fit in a curve, and by using some cost function. I think I used a mean square error over here, and then it converges to some solution which seems to be correct. And so this worked for the velocity scale, but for the shape function, I again ran into problems when it came to symbolic regression. So I did some approximation, and I found out that I can approximate where this maxima is occurring for this shape function, and I empirically fit an equation which has inputs given over here. It is the boundary layer depth divided by Ekman depth as well as Monino-Markov depth. And using this approximation, I was able to get a nice expression, or at least something which is simple and well constrained equation for this G sigma. But overall, I was able to replace the networks which predicted G sigma and V with some approximate equations. And here are the results. As in this one is the control scheme or the output from the control run. This one is with neural networks, and this is for the equations. As in, with equations, we could get some similar reduction in the bias. It's not as good as neural networks, but it's still much better than the control scheme. And with equations, the good thing is that because there are few terms, it's much cheaper to compute than with neural networks, which has roughly 1000 to 2000 parameters, which have to be computed at each grid point and each time step. But then the question remained, as in, what caused this bias reduction? Because, well, yes, the physics have improved, but can it be pinpointed to some term which was missing? And it's very difficult to do that in a quarter degree global 3-dimensional simulation. So to investigate that, can I point out to some term missing in the baseline scheme using equations? I did some single column model experiment. So I want you to focus on this red box over here. As in, what I've done is I have run single column model simulations, which are forced at the surface, and they are forced by fluxes, unlike the quarter degree model, which is where the fluxes are parameterized. And in this experiment, I have changed the latitude as well as changed the heat flux. And So this is the summer mixed layer depth. So I had a hypothesis that this is due to the surface heating conditions. So I just gave a stabilizing surface heat flux, and I found out that the velocity scale for the baseline scheme doesn't respond properly to the surface change in the surface heat flux. And so that baseline scheme is given by this crosses over here. So this cross represent the baseline scheme, but the new diffusivity which comes from the neural networks or the equations uh, do respond to the change in the heat flux. So for example, if you just look at this latitude, if you increase the heat flux, then the velocity scale reduces. That is the diffusivity is reducing, and this agrees with our understanding of turbulence. As in, if you have a stronger stabilizing heat flux, then it will reduce mixing, right? And so which means that probably this is the reason why we are seeing this reduction. And if you compare this experiment with the equations that we have in the baseline scheme for the surface stabilizing conditions, the velocity scale is only a function of u star, and there is no buoyancy term over here. But in the new diffusivity, there is this parameter x which has the buoyancy flux. So when you increase the buoyancy flux, the velocity scale does decrease. And probably this is the reason why the baseline scheme was was mixing more than required in the tropics, where we have strong heat fluxes. And by having the new diffusivity which appropriately reduced the mixing, that sort of there was a fixing of the bias or something. And so this so I think this is the most probable reason of why there was a bias reduction. And with interpretable equations, we were able to compare the new diffusivity with the baseline diffusivity. And because this new diffusivity is or the new velocity scale is very close to what the networks were doing, I can say with some confidence that this is what the networks were trying to approximate in the neural networks, or in those neural networks. And so to conclude, complexity in higher order schemes can be captured and brought into first order closures, because we want to assess the impacts on longer timescale simulations without going for shorter time steps. The bias reduction was roughly 30% around the equator, and overall 5 to 10%. The good thing was no other biases were worsened. So I showed the summer mixed layer depth, but the winter mixed layer depth did not change, or the bias did not worsen. And these were ocean only experiments. So this is not a climate experiments. So I do not know what happens if you run this in a climate model. And equations that replace neural networks do it at a much lower cost. Conservation laws are satisfied because we are still within the traditional framework. And most probably, the enhanced diffusivity has lower magnitude for surface heating conditions, which could lead to the improvements in the summer mixed layer depth. And so by showing this paper which Julian showed in the slide, this is the same paper. And with this, thank you, and I'm happy to take questions.
Thank you very much, Aakash. Questions? Two of them already.
Thank you, Aakash, for awesome presentation. And also, I really enjoyed this paper. So I'm going to ask a question about the paper. I'm very sorry. So here you you wrote that you had a problem with generating data from Gotham for mixed layer depths between 200 and 300 meters. I didn't really understand that part. So if you could talk a little bit about it, and maybe just make a general comment about the limitations for the neural network based on the training data, that would be great. Thank you.
Thanks for reading the paper so carefully. So the network has some inputs, right? In my case, it's Coriolis, U star, buoyancy flux, and boundary layer depth H. in the training data, the training data is single column model, so it has some fixed height. I think it's 800 meters or 600 meters, whatever, which means the training data doesn't have boundary layer depths below that value, obviously. But when you put this in a production model such as global mom6 or whatever, nemo, whatever, the boundary layer depth could go below that. Especially in the EPBL scheme where it's an iterative solver, there's an estimation of h which could be at the bottom or the mid column, whatever. And so there is a problem of generalization, as in h could go out of bounds. And so this has been a concern, as in what if h input to the network goes out of bounds, then how will the network behave? And but luckily I found out that if you split this kappa into these three components, right, G sigma, H and V, then G sigma was not sensitive beyond some certain level, or certain like 300 or 400 meter. And so capping at that point made sense. And so that was why I chose those numbers, because it was insensitive beyond that. Okay, thanks. Another limitation comes from physics. So for stable conditions, you cannot get deeper boundary layer depths. Sorry, you can get boundary layer depths deeper than the Money-Nabokov depth. But in the model, it could go deeper because of this iterative solver or some other problem. And so there has to be some way of getting around that. Yeah. Thanks.
Thank you. Second question.
Thanks for the talk. I was wondering what's the size of the training dataset do you need? Because you're relying on, if I understood well, on the training dataset produced by a second order closure, which actually are closures, so they have their own biases. For example, you mentioned the non-local terms or this kind of thing that are not necessarily present.
Yeah.
But I guess that if you are using this second order momentum, it's because it's kind of cheap to obtain. So is there a trade-off between having cheap reference but in a large producing a large data set?
Yes. So I mean, the ultimate ground truth should be LES, I think, because that has better turbulence in it. But I want to generate training data which spans the phase space seen in a climate model. So it should see that U star as well as buoyancy flux for each latitude. And so it's difficult to have LES for all those cases. And so a trade-off is going for this intermediate complexity models, right? And we assume the ground truth to be second moment closure. So I used Capsulon, and I agree with you, it has its own biases, but the assumption is that at least it's better than the first order closure. And it doesn't have non-local terms, so that is one issue. So yeah, so effectively whatever biases and problems are there in your training data will creep into your network and into your model, but the hope is that at least it's better than what we were using in the first place.
Actually, I do have a question just so that it gives people a bit of time for thinking. You haven't commented much on the question and likely issues related to the actual implementation of the neural net in MUM6. So any general comment on this or general experience gain?
Yeah, so well, I can talk about my experience.
Yeah.
So one challenge is that these networks are trained in Python, right? So you use PyTorch or some other library, and it's easy to run them in Python, but the climate models or the ocean models are in Fortran, and so they have to be somehow bridged. At least for my case, I found out that the networks that you're seeing over here are small, as in it's a simple MLP network with 2 layers in between and 13 nodes. So it's very small and compact, and the only thing required when you want to use them in a Fortran model is that you just require a feed forward calculation, right? So you just need to multiply matrices, and so in that case it was easier to just code in the feed forward multiplication as subroutines. and Fortran and MOM6 or any ocean model is already equipped to read the weights and biases through netstdf files. So I went with that kind of implementation. So everything is in pure Fortran, but the training happens in Python. Probably there are better ways. If you have some sort of complicated networks, then maybe bridging is required, and there are other people working on that. Yeah, thanks.
Thank you.
Thank you, Akash. Very interesting. I'm just wondering, maybe it's very naive. You're using two different sets of variables for training the two length scales. Well, G sigma and the velocity scale. How do you choose them, or is?
So this is the usual way in which diffusivity is designed, right? For example, if you look at KPP scheme, there is a shape function, there is a h, there is a velocity scale, and going with the same framework or splitting the problem into two terms, it's easy to diagnose if something goes wrong. So yeah.
U star, B0 and H for G sigma, and then F prime, U prime, and B0 prime. So you.
Oh, yeah. So there are two sets of these inputs, and the only reason is that again, H could go out of bounds, but G sigma was found to be insensitive, but V was sensitive when you go out of bounds. But then I realized that at least in the training data, if I average over H, it was similar. The value was same. So not including H was much better than including H and worrying about out of bounds.
So you had to try it. You did some trying, and then you.
Yeah. Okay. There's a lot of trial and error, and yeah.
Yeah. Yeah, Aakash, thank you. Very nice talk and very interesting paper. I think my question is somewhat similar to Diego's. It's about whether you're over constraining the fit, and so one of the lessons from machine learning, as I understand it, is that it's a bit dangerous to put too much of your experience from past GF. A problem to over constrain the fit of the machine learning, and this division into G and V looks a little bit like that you're sort of solving sub problems rather than one problem, and perhaps that you're over constraining the inputs that you're putting in. But perhaps you could just comment on that a little bit and your thoughts on that.
Well, I mean, the problem of overfitting or underfitting, the machine learning community has taken care of it by having training data and testing data. So you split the data, and then you train on the one data set, and you test on the other data set, and you randomly do this again by sampling again and again. So in that sense, the error or the loss were showed that it is not overfitting, at least separately for G sigma and V. And I did this multiple times also by changing the random seed and having multiple networks. So I'm trying to be very careful about not overfitting. Overfitting could come in if you have a very huge network, like maybe deep neural network or something. Then overfitting might come in, but these networks are small, so there is a low chance of, I think, overfitting. But again, the training and testing helps you in that.
If I may just jump in, maybe also connected to your question, I guess, Max, there's the somehow if you're making like strong assumptions as to the form of the function, you're actually restricting the functional space where you're looking for the question, and in many circumstances that helps for stability, things that you don't. That's so here basically, if you restrict, you will need like less data for training, plus you're sure that you can enforce some properties of the solution you get in the end. So there's a trade-off there, but certainly the question of knowing to what extent a new assumption is needed or overly constrained is something pretty open. Yeah.
But for the equation discovery part, that problem is definitely not there, because there are just 15 parameters or something, which is roughly the same as a second moment closure or less than that. So, and production model neural network won't go in. So, yeah.
It's me again. So you mentioned this equation towards the end, and as you said, one of the biggest criticism towards neural network model components is that we cannot get any physics out of it, but you actually managed to do that. So I was wondering if based on this equation that you get, is it possible now to drop the neural net and try to construct a new parameterization based on that?
Yeah, definitely. So when I said that the second plot is neural network and the third plot is equations, that is what exactly it is. The now, because I have equation for G sigma as well as velocity scale, we can just get rid of the neural networks, and we can directly go to equations. In fact, that is what you see over here in this figure, as in this simulation is run only with pure equations, and it is much cheaper than running a neural network.
By the way, I had a question, probably naive. Is the structure of the equation V equal blah blah blah? Can you recognize some structural resemblance with higher order parameterizations, or does it remind you of something? Did the machine learning thing exhibit a function that reminds you of something?
I don't think so, because this is a scalar quantity, and second moment closures have a vector for velocity. So they usually have a velocity scale which maybe has some value at the top, and then it goes down. So because in second moment closures it's square root of TKE, and so it's tough to have a one-on-one correspondence between this form and some TKE based equation or closure. But to be honest, this is one way of getting velocity. There could be some similar compact equations, and you could get multiple of them.
Yeah, that's it.
And
there might be some log functions or any kind of...
Oh yeah, sure. Yeah. So there could be different ways of getting the same velocity, the same prediction. But I think the main point would be, if all of them have this buoyancy flux, then it probably will fix the problem.
Okay.
Yeah, just building on Thierry's suggestion, I mean, perhaps you could go back to the large eddy simulation type things and see whether this sort of parameterization, has some basis to it.
Yeah, sure. Yeah.
Is there any question online? I haven't checked.
I haven't checked either. Sorry for that.
Nope. Not yet. Anne-Marie?
Well, thank you for this very interesting talk. I wonder, I mean, somehow the fact that you have to bring in the buoyancy forcing means that EPBL fails, because EPBL is supposed to represent the response of a boundary layer to the surface forcing, wind and buoyancy forcing. So somehow this is a failure of EPBL. Do you have a comment on that, or how would you fix it, or why this failure? Because after all the energy and the skills that has been put into developing it?
No, so there are two parts of EPBL. Part one is estimating the boundary layer depth, which has everything, which has effects of surface stabilizing, buoyancy, destabilizing, friction, velocity, etc. So the energy calculation takes care of all of these terms. The step two is imposing a diffusivity profile where the approximations come in. And there this problem came up, and that's what I fixed. So the original EPBL, which has the energy calculation, that could be assumed to be correct. It has all those effects.
I may have a small question here too. So, so the way how you propose to deploy ML here is really like targeting a specific aspect of a pre-existing closure where we know that there's a weak point, because because I guess the developers of EPBL knew that this was something where it was big approximation, right? So, do you think that this question of how we identify the weak points of our models is also something that we could approach more systematically, maybe in connection with the discussion we had this morning. And how would you therefore recommend we move forward for identifying those aspects of our models that require like being revisited?
Yeah, I think going for a neural network as a step one could be a good way, because if you have the data and if you can train a neural network, and then does it perform anything better than the baseline scheme? That should be one step, I think, because if it performs better, then definitely we are missing something, and then that would give us some insight into what is going correct, what is going wrong, and where should we target. So, for example, in this improvement, the tropical regions improved, but the Southern Ocean did not improve. And so that means there are some processes in the Southern Ocean or some other processes which are not affected by maybe the boundary layer mixing scheme. And so I think there is some sort of trial and error involved, as in go with step one, take a neural network which has probably learned something better, and then get some insight from there. I think that's the way to go, at least.
Okay, so you mean like some sort of an iterative process where you get like a fully pure ML approach and physics-based approach on the other side, and trying to find like interesting intermediate steps between the two.
Yeah.
And so far, I guess the only like a published pure ML vertical physics scheme is the one by Liang, right?
Yes.
That's the only one so far.
But I don't think their work shows long integration timescales. So they have vertical mixing.
But that's multi-year still. That's at Ocean Station Papa, right?
It's at Ocean Station Papa, yes, but I don't think it's a climate model.
No, sure.
Yeah. But yeah, so that's the other work.
A comparison with your schemes could be interesting indeed.
But that is for KPP. So they have targeted parametric uncertainty in KPP by assuming that one component or some component should have a better equation.
Or maybe we should discuss that offline. I was referring of a slightly older paper where they actually replaced the entire vertical mixing scheme with that's Liang et al. 2022 or something. We're actually working on this at the moment, implementing it in NEMO. But I guess we're getting close to the end of this discussion. Thierry, what do you think?
Yep.
Cool.